Okay, so today we want to go ahead and look at section 3.3. 3.3 is where we're going to deal with a couple of identities. The first one is the cosine of a sum formula, and the other one is the cosine of a difference formula. Now, again, if you look in your textbook, on the back cover here, notice that we've covered everything on the left-hand side of the page here. And now we're starting to look at the right-hand side. So we're going to look today at the cofunction identities and the cosine of a sum or difference. So those are the two things that we're going to look at today. There are the books here. Now then, we're going to take some time today, and we're going to develop first of all, the cosine of a sum or difference formulas. So to do that, I'm going to go and just look at a different paper. You can use the backside of the paper or something like that. Let's draw a little circle. On the circle will be on a coordinate grid. There we go. So there is our circle. We're going to look at several different points here. This first point, I'm going to put right here. And the line connecting those two, good deal, that's going to be called point A. Now, this point A is going to have some angle alpha here. Now, this alpha means that the coordinate for A, if we consider this the unit circle, then the coordinate here would be the cosine of the angle alpha, comma, sine of the angle alpha. Because remember, on the unit circle, the x-coordinate is cosine, the y-coordinate is sine. Good deal. I'm also now going to say, let's take some other point here. Let's call that point B. And this point from the terminal side here to this terminal side here, that angle right here will be called beta. Now, notice that the overall angle here from the initial side of the positive x direction all the way to the terminal side, then that overall angle is alpha plus beta. So you have to add those two together. So as a result, the coordinate B would have the coordinate of cosine of the angle alpha plus beta, comma, sine of the angle alpha plus beta. So that would be the coordinate for B there. It's cosine of alpha plus beta and sine of alpha plus beta. Now notice, I'm also going to have another point here. And this other point will be where we have this angle here, and I'm going to call that negative beta. So in magnitude, this angle should be the same as this angle. Notice, though, that one's going the positive x direction, one's going the negative. So one's going the positive direction, one's going the negative. So I'm going to call that one a negative beta. But since this one is from the positive x direction going down, this is actually the angle that we're looking at here. And on the unit circle, again, the coordinate here, I'm going to call that coordinate C. The x-coordinate is cosine of the angle. So this is going to be cosine of the angle, which is negative beta, comma, sine of the angle, which is also negative beta. But notice that cosine of negative beta and sine of negative beta, with that negative on the inside, I can use the fact that cosine and sine are even and odd functions. So C would also be thought of as just cosine of beta, because cosine is even. That means the negative sign in there just goes away. Comma, sine is odd, so that negative here goes on the outside, which gives me a negative sine beta. So there you go. That would be coordinate C. Now then, sorry, back circle. There we go. notice something, that the distance between this point here for B and this point here for A, in other words, the distance of that chord, so it's called a C-O-R-D, a chord, sorry, C-H-O-R-D. So it is a chord. Now that chord has a distance, and that's just the distance from B to A, and we'll talk more about that in a second. Actually, was that the right one? No, sorry, my apologies. You're gonna want to erase that one. My apologies, I was wrong. What I'm gonna do is I'm gonna introduce a point D here as well. Point D is gonna be the coordinate 1, 0. There we go, that's better. Now then, now we can start doing the chord. The chord from B isn't going to A, it's going to D here. So from B to D, that is the chord that we're looking at. And also, if I do another chord from A to C, that's also going to be a chord. Now, chords are any line segments that begin and end on the circle itself, but do not go through the center of the circle. In this case, the origin. Notice that these lines start and end on the unit circle, but they don't go through the origin. So that's why they're chords. But here's the thing. The chord, the first one that I wrote down, is just from the line segment BD. And the second one that I wrote down was from the line segment AC. But here's the thing, those two chords must have the same length. Why? Well, if we come over here, notice that the angle from this terminal side containing D to this initial side containing D to the terminal side containing B here, that overall angle is alpha plus beta, right? Then over here, from this point here to this point up here, notice that's still just alpha plus beta for that central angle. And remember that for triangles, and that's really what these are forming here, right? So let me use the tail there. So this is forming this triangle here. In triangles, angles, the larger the angle, the larger the side. The smaller the angle, the smaller the side. But notice that we also have this triangle here. And notice those two central angles are the same. That means that there's sides that are opposite, that side and that side. They have to be the same as well. Does that make sense? Good deal. So, segment BD, segment AC, the lengths of those must be the same. However, the magnitudes of these are interesting. Now, the magnitude is just the distance between those 2 points. Now, notice that B is from cosine of alpha plus beta, sine of alpha plus beta, all the way to 1, 0. I want to find that distance. And then for the other one, we go from cosine of beta, cosine negative sine beta, all the way to cosine alpha, sine alpha. We want to find that distance as well. So we're going to find these two distances. So the distance between B and D is equal to the following. Now, I'm going to just use the distance formula, which is the square root of the square of the sum of the difference of the square root of the sum of the square of the difference of the components. In other words, looking at the x's for B and D, the x's are cosine alpha plus beta and 1. And then for the y's, they're sine of alpha plus beta and 0. So I'm going to do this one as the second one, this one as the first. So this is going to become, in parentheses, cosine of the alpha plus beta minus the x coordinate of D, which is 1, all squared, plus, and then over here, the y coordinate here is sine of alpha plus beta, and the y coordinate here is 0. So it's going to be plus sine of alpha plus beta minus 0, all squared. Now the segment AC, its length will be done the same way. We saw the square root of the sum of the squares of the difference of the components. Well, coming over here, what 2 points am I looking at? I'm looking at cosine of beta and cosine of alpha. The difference between those, I'm going to do the cosine alpha minus cosine beta, and then sine alpha minus a negative sine beta. It doesn't really matter what order you do it in. That's what I'm going to do it in here. So this will give me, in parentheses, cosine alpha minus cosine beta, all squared, plus, and over here for the y's, that would be sine alpha minus a negative sine beta. Now, minus the negative means plus sine beta, all squared. Good deal. Now, notice that we have said that these two are, in fact, the same length, right? That means that segment BD's length and segment AC's length, they should just be set equal to each other. So basically what's going to happen is we're just going to set the first one equal to the second one. I'm going to come down here and do it. So this is going to give me cosine, sorry, this helps with the big square root here. So cosine of alpha plus beta minus 1 all squared plus, and over here, sine of alpha plus beta minus 0 is just sine of alpha minus beta, alpha plus beta, right? So that'd be sine of alpha plus beta all squared. So that's BD there. Again, all I'm doing is I'm just rewriting that, except without the minus 0. There's no reason for that. And over here, we're going to set the right-hand side equal to the AC here. And that was parentheses cosine alpha minus cosine beta all squared plus parentheses sine alpha plus sine beta squared. Now then, notice that the square roots on both sides effectively cancel each other. In other words, you can just square both sides here. Square the left-hand side, square the right-hand side. Square roots and the squares cancel. We're just left with what's inside the radical called the radicand. Now, we need to go ahead and simplify this a little bit. On the left-hand side, I'm going to square cosine of alpha plus beta minus 1 using the binomial squared formula. So to do that, I need to square everything in there. That's going to give me cosine squared of alpha plus beta. Leave some space here because we need that middle term here. And then square the last term. Squaring the last term gives us a plus 1. Well, what about that middle term? Notice we need to multiply these two things together. What is cosine of alpha plus beta times negative 1? Cosine. Negative cosine of alpha plus beta. Now double the coefficient, that makes that negative 2 cosine of alpha plus beta.
Well, what do we double the coefficient?
Because of the binomial theorem. A plus b squared is a squared plus 2ab plus b squared. And over here, notice that sine of alpha plus beta all squared. This is just one term, squaring, so I'm just going to bring the square inside, making that sine squared of alpha plus beta. Good. That's the left-hand side. Equals, now on the right-hand side, I need to square both of those binomials as well. So cosine alpha minus cosine beta squared, when you square everything, you're going to get cosine squared alpha, leaves some space, a decent amount of space, plus cosine squared beta. Then multiply these two things together. What is cosine alpha times negative cosine beta? Well, it's negative cosine alpha cosine beta, right? Double the coefficient, that makes that minus 2 cosine alpha cosine beta. So cosine alpha minus cosine beta all squared is cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. Now let's square the sine alpha plus sine beta. So squaring everything there, that leaves me with a sine squared alpha. Leave some space. I'm gonna have to go to another line here. Then we'll square the sine beta, which gives us sine squared beta. Then for the middle term, we multiply these two things together. Sine alpha times sine beta is simply sine alpha sine beta. Then, of course, we're going to double the coefficient, which makes that plus 2 sine alpha sine beta. Wonderful. Well, here's the thing. Notice, first of all, on the left-hand side, that I have cosine squared alpha plus beta and sine, what did I do? It's a plus there. Plus, and then here, sine squared alpha plus beta. What is cosine squared plus sine squared? 1. It doesn't matter what the argument is, as long as that argument's the same for both of them. Cosine squared plus sine squared is 1. So those two combine to give us to give us just 1 there. So it's going to be 1 minus 2 cosine of alpha plus beta plus 1. And that's the left-hand side. And again, that came from just doing cosine squared plus sine squared. What about the right-hand side? Now notice something else. Over here, we have the cosine squared alpha here and a sine squared alpha here. What's cosine squared alpha plus sine squared alpha? 1. So those will just produce 1. Plus, and over here we also have cosine squared beta plus sine squared beta. What's that? 1 as well. So the cosine squared alpha plus sine squared alpha was 1. The cosine squared beta plus sine squared beta was 1 as well. Notice that nothing else will combine. Those two are not like terms, so we just need to rewrite those. So this would be minus 2 cosine alpha cosine beta, and then plus 2 sine alpha sine beta. Good deal. Now on the left-hand side, notice that the 1's combine to give us a 2. So it's 2 minus 2 cosine of alpha plus beta is equal to, on the right-hand side, those two 1's combine to give us 2. And then minus 2 cosine alpha cosine beta plus 2 sine alpha sine beta. Fantastic. Here's the nice thing. The 2's cancel each other. I'm not going to rewrite all this again. You could if you want, but I'm not going to. But notice that what I want to do is I want to find the cosine of a sum. And that's what this is. It's the cosine of a sum. To get that cosine of alpha plus beta by itself, I need to go ahead and divide by that -2. But if I do that to one side, I do that to the other side as well. So the left-hand side, as a result, would be cosine of alpha plus beta is equal to the right-hand side. Notice the -2 divided by -2 is a +1. So it'd be cosine alpha cosine beta. And then minus the 2's cancel, leaves us with sine alpha sine beta. And there we go. Here's what we wanted. We know that the cosine of alpha plus beta is equal to cosine alpha cosine beta minus sine alpha sine beta. Fantastic. This is the cosine of a sum formula. Notice that this is not cosine of alpha plus beta equals cosine alpha plus cosine beta. In other words, we can't distribute the cosine to it. It just doesn't work that way. This is not a linear operator. So, how can we memorize this? Well, first of all, notice that the order stays the same, alpha, beta, alpha, beta, alpha, beta, right? But how can I know cosines and then sines together? Well, first of all, cosine overall, is that even or odd? Cosine even or odd? It's even. So we need stuff to multiply together to give us evens because we have a sum. So these would both have to be even, and even when you add them together, right? Why? Because you can only when you add up all evens do you get an even for your function. So as a result, notice that multiplying two evens together will give us an even, and two odds together will give us an even as well. But that doesn't tell us which one is going to be which, because with that minus order matters here. So just remember cosine is the x coordinate, so it goes first. Sine is the y coordinate, so it goes second. Another way of remembering that minus there as well, cosine, there's an O in there, meaning opposite between them. This is just how I've memorized this over the years. You can find your own way of memorizing it, but this is how I did. Good? That was weird. Fantastic. Now, that's cosine of alpha plus beta. That's the cosine of a sum formula right there. Cosine of alpha plus beta is equal to cosine alpha, cosine beta, minus sine alpha, sine beta. There's also a cosine of a difference formula. Now, I can get there from this formula itself. Here's how. Instead of using beta, I can use a negative beta instead. So in other words, if I had cosine of alpha plus negative beta, well, using the formula here, notice that would tell me that would be cosine of alpha times cosine of that negative beta minus sine alpha times sine of that negative beta. Now, plus a negative is just minus, right? So it means that we're going to have cosine of alpha minus beta. That's exactly what we want to figure out here, the cosine of the difference. But over here on the right-hand side, notice that this negative beta, well, because it's a negative on the inside, we're working with a trigonometric function, it can either go away or it goes on the outside, one of the two. Is cosine even or odd? Even. What even means is that negative sign just goes away, or you can add it in anytime you want. So this means that cosine alpha, cosine beta is what we're left with there. And then what about sine? Is sine even or odd? It's odd. And with odd, you have to move that to the outside. But two negatives as a result will give us a positive. Sine alpha, sine beta. And there you go. There is your cosine of a difference formula. It follows directly from the cosine of a sum formula. Good. Any questions about that? No? The same reasoning applies for the memorization. Notice that if that's a minus, that's a plus. If that's a plus, that's a minus because I'm working with cosine. Good deal. Any questions about these? Outstanding. I'm going to come back and prove the cofunction identities here in a little bit. For now, though, we're going to look at the following. Find the exact value of the following using a cosine of a sum identity. Now, notice that this specifically says to use the cosine of a sum identity. So cosine of 75 degrees. Notice that 75 degrees is not one of our special angles, right? What are the special angles that we know, just in degrees? Well, we know the degrees of 0, 30, 45, 60, 90, 120, 135, 150, 180. Now that's just the first half of the unit circle, right? Just keep going and you would get the other degrees that we know for sure. Notice though that 75, that's definitely not in there. Oh, I forgot my degrees on there, didn't I? Degrees. There we go. So 75 degrees is not in there. So it's not something we know just off the top of our head, but it is something we can figure out now because we're looking at the cosine of a sum formula. Out of curiosity, do you see any of these angles that add together to give you 75 degrees?
30 and 45.
30 and 45, right? So this is the same thing as saying, what is cosine of 30 degrees plus 45 degrees? Now, it doesn't matter if you do 30 plus 45 or 45 plus 30, it's the same thing. Because addition, there is a commutative property there. But let's use the cosine of a sum formula. Remember, cosine alpha, cosine beta, minus sine alpha, sine beta, right? So this would be cosine of the first one, 30 degrees, times cosine of the second one, 45 degrees. And then minus sine of the first one, 30 degrees, times sine of the second one, 45 degrees. Good deal. And now you just have to know what these values are, which is why you need to memorize the unit circle, right? Right. So, what is cosine of 30 degrees?
Square root of 3 over 2.
Square root of 3 over 2. Times, what's the cosine of 45 degrees?
Square root of 2 over 2.
Square root of 2 over 2. And then minus over here, what's sine of 30 degrees?
1/2.
1/2 times sine of 45 degrees? Square root of 2 over 2. Good. Now notice that we're multiplying and then we're going to subtract, right? Now with the multiplication, notice that nothing in the numerator cancels anything in the denominator. So I need to just multiply straight across. What is the square root of 3 times the square root of 2? Square root of, what's 3 times 2? 6. You were thinking addition. What's 2 times 2? 4. So it's square root of 6 over 4. And then minus, what about over here? What's 1 times the square root of 2?
1 square root of 2, or just square root of 2.
Square root of 2 over 2 times 2? 4. Fantastic. Now notice that the denominators are the same, right? Means we can combine them as square root of 6 minus square root of 2 all over 4. There you go. We now know that the cosine of 75 degrees is square root of 6 minus square root of 2 all over 4. And we now have an exact value for cosine of 75 degrees.
How come we would have put like plus or minus?
What do you mean?
I thought you said when we have like the square root of something, it's plus or minus.
Be careful. We only use the plus or minus if it says x squared equals something. And then we use the square root property.
Oh,
These, they're just square root of whatever it is.
okay, so it's just there.
Mhm.
Okay.
Good. Other questions? No? Outstanding. The next one we want to look at is cosine of 105 degrees. Now, looking at our special angles up here, do you see any that would add up to be 105 degrees?
60 and 45.
60 and 45. Those are the two values that we would use. Or if you really wanted to, we now know 75, right? And we also know 30. We could just do 30 plus 75. But I'm not going to. I'm going to use the 45 and 60. So cosine of 150 degrees, 105 degrees, not 150. Cosine of 105 degrees is equal to the cosine of 45 degrees plus 60 degrees. I want you to use the cosine of a sum formula to go from there. See what you get. I dare you. Where do you see those cosine 60 degrees? So the cosine of 45 degrees plus 60 degrees is the cosine of 45 degrees times the cosine of 60 degrees minus the sine of 45 degrees, sine of 60 degrees. So the cosine of 45 degrees is what? Square root of 2 over 2. Cosine of 60 degrees is 1/2. And then minus sine of 45 degrees, square root of 2 over 2 times sine of 60 degrees is square root of 3 over 2. Multiply straight across, that gives me square root of 2 over 4 minus the square root of 6 over 4. Combine them into a single term as square root of 2 minus square root of 6 all over 4. And there we go. Any questions about this? Not yet. Good deal. Number 3, find the exact value of the following using the cosine of a difference identity. Now, again, we have to read what's asked for. It is the cosine of a difference identity. So cosine of pi over 12. Notice that this is using radians, right? So you tell me, what are these special angles for radians? Here, I'll do the hard one. There you go. You're welcome. What's the first? What's the next special angle? It's what?
Pi over 6.
Pi over 6, then
Pi over 4.
pi over 4, then
Pi over 3.
then
Pi over 2.
then
2 pi over 2. Or 3 pi over something.
3 pi over 2. Yeah.
Then it's fine.
Did I say it wrong?
No,
And then it's not fine?
no. I don't know. Oh, I didn't hear what you said.
Oh, 5 pi over 3.
No. 3, wait, did I say 3 pi over 2? That's not it.
2 pi.
No, it's 30 degrees. It's 100 and
5 pi over 6.
120 degrees.
I don't know.
120 degrees
I know
is,
it's right away.
I think it affected on the rating.
no. 2 pi over 3. There we go. 3 pi over 4, then 5 pi over 6, then pi. Y'all have the unit circles, get them out.
We gotta practice, because I'm just on it next week.
Actually get them out. You don't have to immediately glance at it every time, just know that it's there to use if you need it. Y'all are killing me.
You said we can test over this unit circle this week or next week?
Next week. So cosine of pi over 12. My question is, looking through here, do any of these have a difference of pi over 12?
No.
Well, maybe. But you're probably not going to be able to just see it, right? This is why you need a calculator. So get your calculator out. Never thought I'd hear someone complain so much about getting a calculator. Okay, so notice that we need something over 12, and with subtraction, we need a common denominator, right? So there is a suspicion on my part. It's either pi over 6 and pi over 2. Why am I doing that? There we go. Go away. Either pi over 6 and pi over 2 with a difference there, or it's pi over 4 and pi over 3. I'm not sure which one it is. How can we do that on the calculator? Well, just do on the calculator what's 1 over 6 minus 1 over 2, or 1 over 2 minus 1 over 6. Either way is fine.
1/3.
1 over 2 minus 1 over 6 is 1/3, right?
Yeah.
So is that the same thing as 1 over 12? How about pi over 4 and pi over 3? In other words, 1 over 4 minus 1 over 3. Or 1 over 3 minus 1 over 4. What does that give you? 1 over 12, right? So pi over 4 and pi over 3 are what I'm going to want to use here. These are the two values I want to use. Now notice we want this to be positive, right? So which one should I write down first? Pi over 3, good. Minus then the pi over 4. Because that still gives me pi over 12. And that's the important thing there. Now I'm just going to use the cosine of a difference formula. So this is going to be cosine of the first one, pi over 3, times cosine of the second one, pi over 4, and then plus sine of the first one, pi over 3, times sine of the second one, pi over 4. Now let's figure this out. What is the cosine of pi over 3?
Square root of 3, 2, 1/2.
1/2. Times, what's the cosine of pi over 4?
The cosine of pi over 3. All in answer.
Square root of 2 over 2. And then plus the sine of pi over 3. What is that?
Square root of 3 over 2.
Good. Times the sine of pi over 4 is,
Square root of 2.
there we go. Multiply straight across. 1 times square root of 2 is square root of 2. 2 times 2 is 4. And then plus square root of 3 times square root of 2 is square root of 6 over 4, which combines to square root of 2 plus the square root of 6 all over 4. So the cosine of pi over 12 is the square root of 2 plus the square root of 6 all over 4. Notice we're adding in even more angles than we've already known, all with just these identities. Wonderful. That's the cosine of pi over 12. I want you now to do the cosine of 75 degrees. Using the cosine of a difference formula. In other words, go back and look at the angles and degrees that we know that we listed. Oh, wait, don't do 30 plus 45. We want a difference.
What were you asking this for? Kind of like confused.
Find two angles that when you subtract them, that will give you 75 degrees
Oh, okay.
in your special angles that you already know. Cosine of 20 degrees. Cosine of 45 degrees. Plus the sine of 120 degrees. Sine 45 degrees. We do the degrees as we have the angles here.
Oh, yeah.
anything is not with the values.
Oh, yeah.
So you're done with this, so do cosine of 1 degrees is negative half. And then go from there.
Oh, okay.
Okay, so the two angles that subtract to give us 75 degrees are what? 120 and 45. Now, is there more than that? Yeah, what else could you have used?
35 and 60.
135 and 60. Anything else? Can't think of anything. But yeah, you could have done 135 and 60 as well. But I think everyone did 120 and 45, right? So 120 and 45 here. We have the cosine of 120 degrees minus 45 degrees. So using the cosine of a difference formula, that means this is the cosine of 120 degrees, the first one, times cosine of the second one, which is 45 degrees, and then plus the sine of the first one, 120 degrees, times the sine of the second one, 45 degrees. And then simplify. What is the cosine of 120 degrees? -1/2. Times the cosine of 45 degrees. Square root of 2 over 2. And then plus over here, sine of 120 degrees. What's that? Square root of 3 over 2. Times the sine of 45 degrees, that is square root of 2 over 2. Good. Now notice that -1 times square root of 2 is negative square root of 2 over 4, plus square root of 3 times square root of 2 is square root of 6 over 4. That combines to negative square root of 2 plus the square root of 6 all over 4. Now, if you don't like it written that way, that's fine. You could have also written it down as the square root of 6 minus the square root of 2 all over 4. That would have been fine as well. Good deal. Now, this makes sense though, doesn't it? Because up here, what did we figure out for the cosine of 75 degrees? Square root of 6 minus square root of 2 all over 4. Now, if I had not said using the cosine of a sum or using the cosine of a difference like we did here, you could have just chosen which one you wanted to use to get there. On the test, I'm not going to tell you how to get there usually. I'm just going to say, find this value, find the exact value of this trigonometric stuff. Very mathematical and technical jargon there for you.
So it would be the same answer?
Yeah, same answer, same angle, right? Square root of 6 minus square root of 2 all over 4. Square root of 6 minus square root of 2 all over 4. Same thing. It should be. Because if it's not, we've really screwed up somewhere. Otherwise, cosine isn't even a function. Good deal. Notice that number 4 here is going in the reverse direction. Using the cosine of a sum or difference, we want to simplify these. Now notice we have cosine of 49 degrees, cosine of 4 degrees, plus sine 49 degrees, sine 4 degrees. Well, on this one, notice that we have 2 cosines and 2 sines. They're both even, and the trigonometric function that's even is cosine, right? So this is going to be cosine of 49 degrees and either plus or minus 4 degrees. Should I use plus or minus 4 degrees?
Minus.
Why?
There's a plus between.
The plus means we use the opposite, which gives us minus. Well, cosine means we use opposite of this, which is minus. So this is just going to give us the cosine of 45 degrees, and the cosine of 45 degrees is what? There we go. Easy, right? Don't answer that. Any questions about that?
I didn't know it was even, like by the footplay.
Because cosine's even, right?
Oh, and then, okay.
So
And on.
an even times an even is even. Over here, an odd times an odd is
Even.
even, so an even plus an even is even overall. So it had to be an even function. Yeah, that's how I knew that. Good.
Okay.
Other questions?
Now we should do the same for sign.
Now we'll do the same thing for sine, but in a little bit, that'll be next time. Now we're gonna do this one. For this one, this is gonna be cosine again because they're both cosine and both sine. And anytime they're both the same like that, it's even overall. Now, notice that the sign between these is minus, so that's gonna make this to be a plus, right? Plus what? Well, we have a 2 and a -3, but over here we have a -2 and a +3, right? Here's the nice thing. I can move these around. First of all, I can introduce or get rid of negatives because of cosine. So I guess I probably should do that in between here, shouldn't I? So just to make these the same, I'm just going to introduce a negative sign here for the 2. And I'm going to take away that negative sign here. Just because I want to. Why can I do that? Well, because cosine is even. And over here, minus, I'm just going to keep those the same. Sine of -2, sine of 3. And now that the arguments are the same for the first ones, so cosine of -2, sine of -2, and then cosine of 3, sine of 3. The arguments are the same on both of them now. That means that I can now combine them into a single cosine of either a sum or difference. Now, in this case, because that is a minus there, it means that we're going to use a plus, because it's always the opposite with cosine. And then just rewrite what we have here, -2 and 3. What is -2 plus 3? Sorry? 1. That's as simplified as we get. Do we know what cosine of 1 is?
It's 180 degrees.
No.
What's that a one?
Cosine of 1.
Oh, it's -1.
Nope. Go take your calculators and type in cosine of 1.
At least if it have a degree sign, it was like in radians.
It is the radians. That's cosine of 1 radian.
0.5.
0.54, blah, 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 right? This is an irrational number. And that is the exact value of it, cosine of 1. Cosine of 1 is the cosine of 1. Because we don't have a special angle here, right? So there's no way to simplify this any further. So we might as well just leave it as cosine of 1. Good.
Yeah, I'm kind of confused. Why did you get the 2 negative?
I made the 2 negative over here because the 2 was negative over here. And I made this 3 positive because this 3 was positive over here. These have to be the same. That one and that one have to be the same.
Oh, that's
And also that one and that one have to be the same in order to use the cosine or difference of a sum.
But it has to be, even if we to like take away like a negative and add another one.
Yeah, with cosine, you can either add or subtract a negative. So add in a negative or take away a negative with doing nothing else. I could have also come over here and I could have said, hey, let's take that negative here, move it outside, make that a plus. And over here, I can just get rid of that negative. That would have everything would have been the same thing, right? So if I had done that, that would have been, this is the cosine of 2 times the cosine of 3, and then plus the sine of 2, sine of 3. See that how I'm getting the arguments the same?
Yeah.
And so down here then, it would have been simply the cosine of the 2 and then -3 because it's the opposite. 2 minus 3 is -1, right? Well, you're saying, well, it's the cosine of -1, not the cosine of +1, right? But remember, cosine's even. So I can get rid of that negative, making that cosine of 1. Being even or positive is a very powerful, being even or odd is a very powerful thing. With evens, you can add in negatives, take away negatives anytime you want. Odds just move the negatives inside and outside of it. That's one of the, it is a very powerful thing to be even or odd. I know in 1414, we make very little deal out of being even and odd. Because honestly, it's not all that helpful in 1414. But trig and stuff above, it does become more and more helpful.
So what you're saying is like, if the expression is even, you can add or get rid of a negative?
Anytime you want, without doing anything outside of the function.
And the only time we really do that is just to,
If you need it to be negative or you need it to be positive.
yeah, but like to make it match the, what is the opposite?
In this case, yeah, match the other side's angle.
Oh, okay.
Or as I said, you could move the negative here to the outside like we did here. And why? Because sine is odd. Or you could have thought of it as bringing this negative sign inside. Same thing.
Okay.
Good.
Yep.
Out. Standing in your field. Cue number 5. I dare you. And if you're not careful, I might double dare you. Okay, so looking at this, notice that we have cosine of x, cosine of 5x plus sine of x, sine of 5x. So on these, notice that the first one and the second one, they both have the same argument. So the first of each of the terms and the second of each of the terms, they both have the same argument. So I don't need to deal with any odd or even for sine or cosine. So what is this going to become? Well, using the sum or difference of cosine, this will be cosine of something. Now notice that this is addition, which means that cosine would need to use subtraction here because it's always the opposite with cosine. And so we're going to write down the first one, which is x, minus the second one, which is 5x. What is x minus 5x? Negative 4x. The nice thing about this, though, cosine is even. So that makes that just cosine of 4x. Any questions about this? We've done a lot with just knowing 2 more identities, right? But down here, we can't quite do these. These are asking us to use a cofunction identity to find the following. So let's come back up here and look at our cofunction identities. Now, our cofunction identities are actually nowhere near as bad as what it looks like. Here's what I'm going to do. I'm going to come up here and I'm going to draw a right triangle.
Where's that at?
This is just the page I used to prove the cosine of a difference and the cosine of a sum. Just draw a triangle. Anywhere. On this triangle, this is a right triangle. I'm gonna let this angle here be U. And so this angle up here would have to be pi over 2 minus U. Okay, so I'm gonna let this be X, this be Y, and this will be Z. Z is the hypotenuse. Let me look at a couple of things. What is the sine of U? Well, sine of U using the SOHCAHTOA, opposite is Y over the hypotenuse is Z. So sine of U is Y over Z. Okay. Well, what about the cosine of pi over 2 minus U? Well, the cosine is always the adjacent over the hypotenuse, right? What is the adjacent of pi over 2 minus U? It's Y, isn't it? It's the adjacent. Pi over 2 minus U. And the hypotenuse is still Z. So this is equal to Y over Z, isn't it? Notice then that cosine of pi over 2 minus U is equal to sine of U. Okay, so far? Now let's look at cosine of U. What is cosine of U? Well, it's the adjacent X divided by the hypotenuse Z. So cosine of U is X over Z. Well, what about sine of pi over 2 minus U? Well, pi over 2 minus U is here. The sine means opposite over adjacent. Opposite here is X, the adjacent, sorry, the hypotenuse is Z. So this is going to be X over Z. So as a result, that means that sine of pi over 2 minus U is equal to cosine of U. This is the cofunction identity for sine and cosine here. Now we can go through all this again, looking at tangent, cotangent, secant, cosecant, and all that good type of stuff. But we would just go through all that again, and we would go through and get all of these. Sine of pi over 2 minus U is cosine. Cosine of pi over 2 minus U is sine. Tangent of pi over 2 minus U is cotangent, and cotangent of pi over 2 minus U is tangent. Secant of pi over 2 minus U is cosecant of U, and cosecant of pi over 2 minus U is secant of U. You can just prove all of those from that right triangle that we were looking at. There you go. These are the cofunction identities. The ones that we'll use most often are the sine, tangent, and cosine, although the other three are useful in their own ways. Why are these useful? Well, let's come down here and look at the following. Use a cofunction identity to identify the following. Sine of 5 pi over 12. Well, 5 pi over 12 is not one of our special angles, right? So with our special angles, we'll have to do the following. Now, sine is not even something we're really looking at, right? So we can't use the sine of a sum or difference to get there, at least not yet. Tomorrow, yes, we will be able to, but not yet. So instead, notice that sine of 5 pi over 12 is the same thing as asking, what is the cosine of pi over 2 minus the 5 pi over 12? Notice that we can always go back and forth between sine and cosine because there's just a phase difference between them. And this is how we write it down. So it's pi over 2 minus whatever that angle is for sine. And what is pi over 2 minus 5 pi over 12?
4 pi over 10.
No. I'm glad we know how to add fractions.
Oh, it's negative pi over 12.
Nope. 1/12 or pi over 12, positive pi over 12. In other words, go to the calculator, do 1/2 minus 5/12. Which gives you 1/12, right? And that, of course, gives us cosine of pi over 12. And at that point, you could use the cosine of the sum or difference formula. In this case, you would use the cosine of a difference formula, which was, as we've already seen, that would be pi over 3 minus pi over 4, right? Right. But we've already done this before, right? Coming back up here, notice that we did the cosine of pi over 12. What do we get? The square root of 2 plus the square root of 6 all over 4. So that's telling us that sine of 5 pi over 12 is square root of 2 plus the square root of 6 all over 4. Right. Refer to previous problem.
Yeah.
And that's our answer. Yes. So it's because the cofunction identity that we're looking at is that cosine of pi over 2 minus u is equal to sine of u.
Okay.
Yeah, so notice that we're given the value of u here, so we're going to plug it in here. What part? Okay. Other questions? Okay, let's look at sine of 15 degrees. Now, notice that all those cofunction identities I gave you in the form of radians. But of course, they work in degrees as well, exactly the same way. So we're going to use the cofunction identity that cosine of 90 degrees minus u is equal to the sine of u. So the cosine of 90 degrees minus u is equal to the sine of u. It's just a difference of replacing the pi over 2 with 90 degrees. That's all. Now here, notice that I'm given sine of 15 degrees. So I'm given this stuff over here, meaning I know u. Plug u in here to be 15. That means that this is the sine, sorry, the cosine, my apologies. The cosine of 90 degrees minus 15 degrees. And so, of course, this would give us the cosine of 75 degrees. And again, we've already done this. Refer to previous problem. So cosine of 75 degrees. What was that? Square root of 6 minus square root of 2 all over 4. There we go. So the sine of 15 degrees is square root of 2 minus square root of 6 all over 4.
I think.
Sorry, square root of 6 minus square root of 2 all over 4. Was that it?
I'm still saying about it.
Yeah. Square root of 6 minus square root of 2 all over 4. Any questions about what I've done there?
So, like, if we've done it before, like on a test or something.
If you've memorized the cosine of 75 degrees, I am more than happy for you just to write it down.
Okay, and we can just write it. Yeah, refer to previous problem.
No, not on this. On your homework. Never mind, not even that. I'm gonna call this instructor privileges. Yes. Mainly for time reasons. Determine whether the following are identities. Cosine of x minus pi over 2 is equal to the sine of x. Well, here's what I'm going to do. I need to determine whether they are identities. I'm going to do that by, well, trying to prove it. Looking at the most difficult side here, we have cosine of x minus pi over 2. That's the most difficult side. That's where I'm going to begin. Cosine of x minus pi over 2. Now, notice that this is not the cofunction identity. Because the cofunction identity is pi over 2 minus u, right? That's the cofunction identity. This is not that. Now, if I flip this around, you have to keep the negative where it is. So notice that this would be cosine of flipping that around, making the pi over 2 go first. But notice the pi over 2 is negative, right? And I'll have to put a plus x there as a result. Well, I don't like having this negative here. So I'm going to factor it out from the inside of the function there. That's going to give me the cosine of, put that negative out front. And what am I left with there as a result? Well, just pi over 2 minus x.
Wait, if, can't you just take away the negative? This is an even function.
You have to talk about why, but yes.
Okay.
So you have to show to get to this far, right? And at this point, you have to realize that cosine is even. And since cosine is even, that negative that we factored out there can just go away. Right? So this is equal to the cosine of pi over 2 minus x. Is that the cofunction identity? Yeah, it is. So the cosine of pi over 2 minus x is equal to the sine of x. Is that what we wanted? Yeah. So yes, this is in fact true. Cosine of x minus pi over 2 is equal to sine of x. However, this is not true in general for all the functions, and we're about to see why. Looking at tangent of x minus pi over 2. That's equal to cotangent of x. That's what we're seeing here, right? We're going to do the exact same thing as we just did. We're going to begin with the tangent of x minus pi over 2. Flip it around just like we did. So it's going to be tangent of negative pi over 2 plus x. Notice that I need to go ahead and factor out that negative there. So if I factor it out, what am I left with?
2.16.
Pi over 2 minus x. Now notice that tangent, is that even or odd? It's odd. So that negative here needs to come outside of the function. And that's going to make that negative tangent of pi over 2 minus x. Still the negative out there, but what is tangent of pi over 2 minus x? Cotangent of x. Is this the right-hand side? No. Can we make it look like the right-hand side? No. So it's just not going to work. So that's it. We're done. The answer is no. So this is just not true here.
How did you go from pi over 2 plus x to pi over 2 minus x?
I went from x minus pi over 2. Oh, you're talking about over here. It was negative pi over 2 plus x, right? That negative is important. So what we're doing is we're factoring this out from both terms. So I'll write it down there, and then this becomes positive, and that will become negative as a result.
Okay, so you factor the whole.
Yeah, from both of them.
Okay.
Yep. Which of course is why it becomes pi over 2 minus x there. Good deal. Good. Any questions?
Wait, so you went right QED on the second one?
No, it was not a proof. Yeah. In fact, it's an anti-proof, if you will. In fact, to really make sure that this is just not true, let's plug in, let's say pi over 4. I could have just said, let x equal pi over 4. So the tangent of pi over 4 minus pi over 2 is equal to the cotangent of pi over 4. Now, pi over 4 minus pi over 2 is negative pi over 2, so it's tangent of negative pi over 4, my apologies. Yeah, negative pi over 4. equals cotangent of pi over 4. Fantastic. What is the tangent of negative pi over 4? -1. And what is the cotangent of pi over 4? 1. Hence the reason that this is not an identity. There only needs to be one place that makes this untrue for this to not be an identity. Now, it can be an equation that you can solve, but it's not an identity because it's not true all the time. Any other questions about that? Outstanding. Hey, guess what? We're done with 3-3. Tomorrow we will continue on to 3-4, and 3-4 is all about the sum of difference and tangent, sorry, the sine of the sum of difference and the tangent of the sum of difference. Yay! We're also happy.